Okay, welcome back to after the break. So now we will continue, and he is going to introduce the some mathematics perception of the deep learning. Do you still have anybody has the question, or you have discussed during the tea time? We can have one or two questions if you have now. Otherwise, you can ask in between as well. No question?
So since there are quite a few queries raised along the direction of deep learning, I thought I will, because many of you seem to be familiar with deep learning and also have queries on it, it may be a good idea that we go into that and we have a chat. Whenever you want, you can just stop and then it's a good idea. I can learn from you also, maybe you know more. It will be nice to talk because see, in a topic where somebody works deep into that, the learning that one will get by practically working on it is enormous. That's a fantastic learning. So I look forward for learning from you, and then you can interrupt and we can talk. Right? I think that would be very nice. So all of us are familiar with deep learning. So allow me to go to the things which we already know so that we can have a nice chat. So what happens? Okay. It is changing here. It's not changing there. It is changing here. Should I use this? It's not changing there. It's changing here. I think we have to share the screen. We have to share probably. Screen sharing has to be done. So allow me to go a couple of steps back again and recall the things that we already know, and we'll build it up so that it will allow us to connect and then talk more about it. Feel free to interrupt me so that I think it will be a nice interactive session. So we all know that which we are going to talk about machine learning, but it is a subset of artificial intelligence. Let's not discuss more about it, and deep neural networks is a subset of that. I will not get into the discussion on that, and the earlier machine learning methods are expert systems, and that's a history of machine learning methods. We will not worry about it. We will not have time. So what is the basic difference between the classical approach and the machine learning? What is actually machine learning? You ask, all of us know what is machine learning. So what is a classical way of learning? Symbolic learning. The AI is either symbolic or machine learning. Both of them are there. Expert systems is symbolic. Whereas machine learning is machines are learning. So what is that? What do you actually mean by machine learning? We all understand. That's a symbolic learning. So if you see what is symbolic, expert systems, which is also AI, is just that. What is that? You have data, you have a set of rules, give the data, and the data will be processed by the rules to give the result. So you have a temperature, you have some details on temperature, blood pressure, all these things, and it is greater than rules. If it is greater than this or less than this, etc., then you have a fever, you have some disease diagnosis. That's symbolic, expert system. That's A. But here, data is given, and you know the answers, and machines learn the rules. Rules are not told, rules are learned. That's what is machine learning. That's in a naive way. So what is this machine learning? You all have, we will definitely have much better answers, because you know what is learning rules. Learning rules which are not known is the job of the machines now. So how do they learn? Since many of you are familiar with deep neural network, I'll answer that in that context. You don't know finding the right weights, finding the right biases. That's what is the learning. It learns. These are not told. So that's machine learning. So that's what is called a rule in a very naive way. So what are the driving forces? If you ask what are the driving forces which enabled us to jump from this paradigm to this paradigm, the state-of-art technology, faster hardware, advances in the software, larger data sets, and mathematics that we have in terms of statistics, linear algebra, optimization, all these things put together enabled us to make a jump from this paradigm to this paradigm. There's a big difference in the two paradigms. Data and the rules are given, you get the answers. Here, data and the answers are known, and you try to find out the right rules. So that any data is given for which you don't know the answers, you should be able to now use the rules that you have learned to get the answer. So that's the machine learning approach, and that's the deep learning method is nothing but a subclass of that. So I will not get into this. This machine learning, very broad categorization, supervised, unsupervised, reinforcement. Let's not worry about it. So a very general rule for machine learning method, you should have a well-defined problem. What a well-defined problem means is that you should have a well-defined goal, you should have a good data, you should have well-defined constraints, and you should be able to, performance metrics should be there, and the data set should be having, data set preparation itself is a challenge. And you need to have a lot of methods. It could be a shallow neural network or a random forest. So it could be any of this, the gallery of these methods. We will not worry about it. So what's a deep neural network? All of us know that there are neurons which are represented, artificially represented by these artificial neurons. You have a layer of them at the input. We have several hidden layers there, and you have an output, a set of neurons. And the information is fed in here. That's why it's called as an input layer. And the information is transformed by affine linear transformations and activation functions. They undergo a series of transformations continuously. They're getting fine-tuned based on, and you are trying to get an output, and you say whether you get the expected output or not. If you don't get, you will say that I'm not happy with the output. How do you say you're not happy with output? So you estimate how far I am from what I want. So that's an error. So take the error and propagate the error back. I have a large error. You please fine-tune yourself and come back. Learning rules. So you have a big error and then propagate as a back propagation. So that's a multi-layer perceptron, the forward and the backward propagation, and you keep on correcting yourself in terms of what are all the affine linear transformation defined in terms of the weight functions, the biases, and the non-linear transformation functions, which are called activation functions. They all get, the weights and the bias will get corrected. That's what is the whole story about. And what sits inside these neurons in the affine linear transformations, what other additional things that you can do inside a neuron that gave rise to a gallery of methods under neural networks. Your understanding of a basic neuron, translation of that will make, if you think it is needed, that's what people taught on various things, at a neuronal level, you get these variations. So that's a very important thing you need to understand. Somebody proposes a neural network, then people came with the GAN, people came with the LSTM. What are all these things? Nothing but changing these things at atomic level, which way you process the data at that level. So what is the atomic level? We need to, so there's a number of things. Nothing but how much of understanding you have put in the atomic level of a neuron. So if you want a naive neuronal representation, which is Spitz-McCulloch naive neural representation, that's what a lot of things work on. People improved the basic Spitz-McCulloch atomic neuron, and they got a gallery of other methods, which are some of these things, right? We'll not worry about that. So let's look at, since some of you had some questions on that, I thought we should basically look at very quickly what is exactly happening. What is the affine linear transformations, how the weights get transformed. We all know it. We will quickly have a look at that part. So what happens here? We have here the layers, input layer, the data is being given. The data is continuously transformed. So that becomes the input for the first layer. For the input layer, it goes to the first hidden layer. A number of neurons are there where neural transformation is taking place. So that's the affine linear transformation in terms of this is weighted. The input that you get is weighted and added with a bias. That's affine transformed. The affine transformed information is further nonlinear transformed by the activation function. That's what happens when it affine transform. That's what is the activation which is taking. Affine transformation is happening inside this neuron, and nonlinear activation functions, HLs, they do that, and that becomes an input for the next layer. So they're all connected to each other, and connectivity is very clear there. So that happens in a continuous manner. Given an input, you have this compositional transformation of the functions that becomes a base for mathematically analyzing these things and probing into the estimates of the error, which is currently state of our topic in looking mathematically how good these methods are. You go to this composition of the function and then say in which spaces actually they are moving into, how good they are, this approximation. So approximation theory for the function composition, operator compositions, etc. will come into the picture there. That becomes mathematically looking at the things, and that's one of the things which currently deep neural networks being looked mathematically from that angle. So now here, if you have this, you need to adjust the parameters in it. So we know that whatever the values that you predict here, if it is not good, you compare, you build a loss function, and if the losses are large, you transmit the message back. There's a back propagation of the error and try to adjust all these methods. That's done by the so-called gradient descent method. It comes in the picture there. So that these weights, etc., are readjusted so that the losses, the functional L of theta, which will get minimized, so that you will get this functional can be physics-based definition. So if it is physics-based, it becomes a physics-informed neural network. How you define your functional depends. Here one can have data, you can have one, and how you minimize this and optimize this function, optimization algorithm like gradient descent algorithms can come into the picture there. Or you can have several other methods come into the picture there. Now, what is exactly happening? How do you go about doing this? The input, that's the little more explanation on that. You have an input layer. This is affine transformation, affine transformed, and that get a nonlinear transform, and a series of this operation take place. What exactly is put up here, that's elaborated here. And when it goes out, that's what is exactly, I have already explained, affine transformation and nonlinear transformation. And what are the various nonlinear functions that I can have for F? So various things. One can have a simple perceptron function or kind of a sigmoid function, tan hyperbolic. One can also come up with a new activation function, and you go back to the basics and see what are all the properties of an activation function. Does it satisfy all the characterizations? And that becomes a mathematical work there. You can really do, and then what kind of approximations you get, how fast it can accelerate, set of things that you can build it up mathematically there. And what happens when you have this, you have the errors. So error is coming, the difference between the computed one and the expected one. So that's a computed and expected, this error. You try to minimize these errors. So therefore you try to take these errors and propagate these errors back. And that's called the back propagation. The errors are sent back at various levels because whatever you get is dependent on all these variables and biases, all the WKs which are used for weighting and all the biases at all the levels are used. So the error at the final level is being simply using the chain rule and you're propagating it back. So that's what exactly happens. That's the forward and the backward propagation. And so that's the way you build up. There are several ways one can build up the loss function. Simply in this case, I have a data loss being used here. One can have physics-based loss. One can have various other losses. If you think whatever is relevant in the context of images, people use gradient losses, people use entropy losses. So you can cleverly come up with your loss functions depending upon your problem. So essentially, you would like to minimize these losses. So that's essentially this algorithm, minimization algorithm, there are a host of them. So one can think of anything. So that's the forward and the backward propagation, which is entirely captured. In a nutshell, that's what is an artificial neural network defined. So essentially, you're trying to learn these weights and learn these biases in such a way that your optimization function is minimized. The losses are minimized. That's the machine learning here. So that's the highlight. What I've already told you, there's nothing but error propagation. Essentially, the thing with the chain rule, because we know that this theta is based on all these variables which are coming from various levels. So if you write it out as a chain rule, that's how this, so you need to have all these things updated. So that's what is updating these values at various interior hidden layers actually mean. So what are all the simple loss functions is that's a data loss, that's mean square loss one can use, or average loss, mean average loss. So what can be the loss functions here? It can be variety, it's physics-based, where the conservation laws are used, differential equations are used, then that will be data loss plus physics loss. So that's what is the physics-informed neural networks all about. And
Weights, this is a very standard.
Standard, correct.
These weights in each layer and the weights in the subsequent layer, are they dependent, linearly independent, and mathematically? What is the, weight in a layer and weight in a...
So clearly the weights are not linearly dependent because you have a nonlinear activation function at every layer, which is obviously affine transformation at a nodal level is being nonlinear transformed by activation function. Therefore, the weights from layer to layer cannot be linearly dependent.
But then what weights in one layer to weights in other layer, mathematically speaking, how different they are? I mean, layer 2 cannot be constructed from layer 1 in the each independent because they are not linear. So what mathematically they say actually? So layer 1 to layer 2, these weights, how you characterize them? So there is some relation dependence between them, but what is that?
The dependency is coming through this. If you were to try to minimize, there's a dependency is coming through. That's what is the chain rule used as well. Sure. So you could make it if the data is stochastic, whatever, there will be different methods. This is for the gradient descent method is one way of tracking this relation. You can have different approach, stochastic then can come in a different way. So this is one standard thing which helps you to get a relation. If you can get the relation by some other means, well, you'll become more innovative. Right. This is something which is standard for all of us to understand. Right? So all of us know chain rule is something which we learn it. And then, so these are the loss functions. This is just a sample. So gallery of loss functions are already there. You can come out with a innovative loss function based on the context in which you are. So that can be a different, so if you look at it, loss function definition itself can become very interesting in different contexts for different areas and different problems. So workflow of machine learning and data learning process, the deep learning process is just you have a data, you have a training and the test set, and we build a model. It can be any one of these models, machine learning or deep learning methods, and you evaluate it, and you make the validate it, and then use it for new prediction. You're happy. That's a standard cartoon on the way it flows. It can be a simple random forest. It can be a deep neural network, whatever it is. That's a standard cartoon for it. It's a flow. So you replace it accordingly by your methods and elaborate it out. You get your algorithms accordingly. But this simple framework is good enough for us to start with. What is the training? What is test data? If necessary, we'll discuss it out later. So now we want to focus on with the simple, naive understanding of the whole thing. Let's try to get into some of the neural networks, deep neural, which have already been used in the context of atmospheric sciences and images in general. We will try to look at them because these are very well established in the literature. So one convolution neural networks, everybody know it. So let's get a little more details for the convolution. You have an input data, it's an image. So that image is getting continuously transformed. So then firstly, it is getting transformed, and which exactly means a feature extraction. It goes on so that the right features are extracted and you pass it on to the fully connected network to finally process it out to get the desired output. So it can be in whichever context, it may be a segmentation context, it may be a super resolution context. So accordingly, you define your layers. So what are these? You can have convolution layers, you can have subsampling layers, so on and so forth. So we will try to get an idea of the operations here. So let me quickly go. So that's a simplistic cartoon on CNN. You have an image, convolution layer, max pool, and dense layer. So how the information is getting transformed in all these layers. So we know it. A good recall on that would be good. So that's essentially what's happening at various layers. The feature extraction is all that is happening there. You have feature extract so that when you regenerate the image, you get a high level features well built into that. So let me straight away take you to the operations. Some standard operations like max pooling. If you have an image, that's the information about the image, let's suppose. And we are using, I just colored it so that just to highlight 2x2 pooling stride. So the max pooling operation means that in this, max pooling is reducing the dimension, 4x4 becomes 2x2, the maximum of this is being put in this pixel there, and so on. 7 is put there, and the max, that's max pooling. Average pooling, take the average of these windows, 4 windows. So that's the operation that extracting the important features which will be subsequently used for reconstructing the image so that the feature is highlighted. You won't lose that. Feature extraction operation is max pooling is one operation. So these are the different operations that we have there. Convolution. So which of the information, you have an input information, that's the image, and you would like to convolve it with a mask of this kind, and you convolve it, giving importance to whatever you want. You can define this mask as per your requirement, and that convolve it, that means you are actually take this and slide it horizontally and vertically down so that you superimpose on 3x3 and multiply entity by entity, entry by entry, and this is what it is going to be like. So if you take this and multiply and add it up, and that's what it will come, and so on. So you slide it horizontally and vertically, this will be, by the convolution operation, you will get a transformed information to be this. The image now, what was originally there, now it is certain features of the image are highlighted here. So what does the activation function do? You have an information here. It's nonlinear activation function, which is of this kind. If it is below 0, it is, you have a ReLU. So that's, if it is below 0, it is 0 down. Otherwise, it's linearly mapped. 25 becomes 25, 0, 2, minus 2 becomes 0, so on and so forth. That's what a nonlinear activation function, a ReLU function would do here. So that's a nonlinear activation, and you can have a dropout layer, which is which is based on max pool. So you have some layer being dropped out, and max pooling is the operation that is done, and that you get that. That's important features are getting extracted. So if you go back to the
Activation function, value and all. So when we are putting 0, that means we are actually losing some information.
yeah,
So, I don't know whether any new polynomial.
there are. I've shown you the gallery of functions. No?
Yeah.
If that is working well, see.
Gallery, see the mostly we are using ReLU or refiller.
Well, if it is that working fine for you, are happy with it, you do that. Finally,
Yeah, but still we are
you want to research on what is the best optimal activation function.
Yes.
You can research on it.
No. That's what I want. Anything happening in mathematics.
We have done some work on. We are not. So you want to come up with people come up with a new activation functions. I think his question is very relevant. Which people regularly use ReLU or tan hyperbolic or sigma function? Why should we know about everything? Is his question. Is that correct?
I'm putting this question whenever I'm in the mathematics conference. So I'm telling the people who are doing the research in this. Some people are working on the wavelength based this activation function, but I have not seen any paper or anything result to that.
Unless it is standardized and recommended by the community, people will not use it. We all know it. Yeah, I think you have people are constructing. Maybe if you want to construct, you can construct. One can work on activation functions. So if you work on activation function, then you are going to approximation theory and energies that it is going to preserve. It will have to establish it out and test it out on benchmark problems, and all that earlier people achieved, you should achieve, and you achieve more than them, then you can sell it. It's a business. Essentially, it's a business.
Linear line kind of. They are already making the
linearity,
but they itself are the linear. Why can't we have non-linear?
The reason here is feature extraction. I want to highlight certain features. These are naturally available, and one can immediately think, I want to highlight what is important. So these highlight that. So they are already working where they are already highlighting. That's the logic. If you can highlight even better by some other function, welcome.
We want to highlight, but we don't know the function. That's what
you have to consider. People have come up with this, correct? What function you need, you have to show the context in which all of them fail. So then you have to see why it has failed. Then comes the research. So generally you have to thinking of a problem which is not existing and you want to come up with it, it is going to be solved.
Our main problem is to capture the extreme events in any of the data, the weather data, right. Whether it is temperature extreme or whether it is precipitation extreme, which we are not able to catch it. And what I feel that when we are going for the activation functions, they are actually losing the information.
Activation function is one entity in the whole process.
Yeah.
So
that is the main
feature extracting for. It can possibly improve, it may not improve. We don't know. So there may be your way that you are representing your data. There may be so many issues at so various things. The method that you use, there are number of methods for extreme event predictions, right? We have done some extreme event predictions using at least 2 different methods. Statistical approaches are there. So it depends whether at what level you are, at the method level or go inside the method and fine tune certain things inside the method. Everything is possible. So, well, I think we will talk about rare events if time permits later. So, okay, now I'm just now talking about super resolution convolution neural network, which is very familiar. I'll not get into a discussion on it because we have little time there. And this method, there are some details. I have talked about what happens in the various layers. I will skip all these details. Super resolution convolution neural networks. So convolution neural network, which we discussed just now, that can be used for super resolution. So that's an example here. That's how a super resolution convolution neural network in its very simplistic representation, it looks like that. You have a data, you have various data is getting transformed there, and you reconstruct it and you get a high resolution. They give a low resolution data, it's transformed to get a high resolution data. So I'm showing these two because these two are going to be used in the context of atmospheric science. Some example. So standard super resolution convolutional neural network, given a data, use the bicubic interpolation and pass it through the various layers before it goes in a dense layer and reconstruction takes place there. Or you can also, that is the standard CNN. You can also have feature feature-based super resolution convolutional neural networks. So why am I showing these two things? Is it is not something, a method one can think of. One thought, I am anyhow extracting features. I want some special feature extraction layer to be added to that. You translate your idea and you get another network. So that's what is happening there. And I will want to show you an example as a GANs. I think I will not get into for want of time. I will skip the details. Generative adversarial networks where I will skip the details because I will not have time for. Okay, so now we will look into the application, a case study of super resolution of atmospheric data using. I have skipped the discussion on RRDBNet and SRGANs. Those are the details which I skipped there. I think that's, we get a feel that these are different networks and which is processing, transforming the data differently. So that's all for us. It means these networks right now mean. And let's not get into these networks and look at the details and get into Fourier neural operator at least for 10 minutes. So time permits, we'll get into this. So in this case, we have for different methods like super resolution convolutional neural network and RRDBNet and which is and SRGANs. So for these two methods, we are used for super resolution. What is the context? The context is, this context is picked up from the literature. So low resolution surface temperature data is given there. In different, these are the highlighted regions. You have JP1, JP2, there's the east and the west portion of Japan, and then you have some portion which is there, NA1, NA2, this box is NA1 and NA2, and SA1, SA2, these are the portions you have. Now, these methods with these parameters which are used for driving this method are used in the super resolution experiment. So I will straight away show you the results. So in this case, what you have, this is the given data. So the given data by different methods. This data is acquired from the European Center for Weather Forecast. So that's the low resolution data. And the different methods that are used, SRCNN, RRDBNet, SRGAN, to get the high resolution, super resolution data. Given this information, will I be able to recover a high resolution data? Yes. In different methods, you will get different high resolution data. That's what it is. And how do you, and this is in the different regions that are shown here. So the high resolution data, given this information, these are all the corresponding high resolution data, which is, I think it is something like, we will see the metrics and what X it is, maybe 5X or 10X, what X we will see. So these are the different methods which are used for getting high resolution data in that. And that's for the other regions that you have, NA1, NA2, and SA1, SA2 is the North America region, this is a South African region. So these regions are being used there. And what you see here is the metrics in terms of root mean square error and mean average errors. So these are only root mean square errors with respect to the ground truth and with respect to what has been predicted by any of these methods. So what we see here is all these methods with respect to for various methods, how they are performing, we are seeing that is the root mean square errors. Please note it, that these are reasonably appreciated. So Chittaranjan, you can note this, these are all the root mean square errors that they are having for these papers here. So I will show you for Fourier neural net. He has done some experiments and we get a root mean square error a little better. So I want you to know these are all currently in the published literature. This seem to be acceptable, and these methods, whatever they have talked about for super resolution of this information, surface temperature data in the different regions, that's what it's all about. So what you have here is root mean square and the mean average error for the entire information with respect to the predicted and the high resolution data. So you start with a low resolution data of that kind, and you come to the high resolution data by different methods. Now you have a ground truth available for it, and then you'll be able to compare that and see how good it is. So this is the performance metric in terms of mean average and root mean square errors that you see here. So these are appreciated, and that's why probably this is published there. And the SRGAN is a highly talked about method, and it has been used successfully in the super resolution in cyclonic study. So let's look at I'll skip the discussion on this, the network as such. So we will look at the output from this study, atmospheric science studies that I have there. In terms of what we have here is a worldwide parameters. These are data for using CAM5 at, this is the information available. This is the surface temperature, sorry, different things. What you have here in the A, we have sea level pressures. In B, you have the temperatures at 200 mbars, and then this is temperature of 500 mbars. And what you have in the D, E, you have a wind velocities and different features, primitive variables that has been there. This is from this data that is available there. As this is the information that goes into the input for cyclone tracking. So this is all the available information. They have projected it out, and then the cyclone tracking, this is the kind of low resolution input you get, and using the SRGAN method, one will be able to get a much clearer picture about the intensity with the cyclone and the internal details of this eye of the circulation. You're able to get much more details. What you see here is a ground truth. That's the SR super resolution image by SRGAN, and this is the, sorry, that's a low resolution image, and that's the generated super resolution image. And the difference between, so I think that's not the difference, that's the ground truth. And C is the generated SR image, and these are detected ones. This is generated by some other method. This is by the, I suppose this is by the SRGAN method. This literature is picked up from this paper just to highlight. Before we go on to Fourier neural nets, I thought I should show that there are several methods which are available in the literature. And this is from a recent literature where this has been successfully used to appreciate the details in the eye of the circulation of this cyclone by these people by using the SRGAN method. These are some details. If needed, we'll get back to this if we get time. So what I wanted to essentially highlight is super resolution method can be used for a complex phenomena like a storm or a cyclone, and you'll be able to get the subtle details inside the eye of the circulation. Also using from the low resolution image, you'll be able to get more information, and you may be able to go more deeper if you can get. So that's about some of the state-of-art methods. Now we will move into Fourier neural operators in.
Sir, among the methods, which are physics informed?
All these methods are based, the kind of the loss functions used in all these functions, they do not involve the physics in that. So physics means, suppose you have the governing equations also coming into the picture there, it's all data-based, right? It's the data-driven methods, so they are not physics-based. You can have a data-driven plus physics-based. Right now, these methods in its form, the way it is published, all completely data-driven. So now let's look even the Fourier neural.
Say that if they are using many multivariable, they call it physics induced or something physics informed. But I don't think this is called as a physics informed. When it is pure data driven, pure data is data driven. There is no physics in. So
this is a data driven. You can have a physics informed data enriched or physics enriched data driven method you can have. So that will become a variability of the method. So that will go into the loss functions. So how you design you put the physics in the loss function.
Not the layers.
That will percolate back into the layers, correct? You could also, if you want to do an architectural variation in the layers at the atomic level of that, that will become a different network, like LSTM or GAN. What is happening inside each neuron? If you vary the operation, that will become an atomic variation to it. And You can also do, there are so many other things. You can also recurrent networks where at each layer you can have the information stored. It can be used. There are a lot of variations in that because that's like you have your understanding of your neuronal cells. So when I process, I may also use of past memory in processing it. So just that understanding, get to the time series analysis or using recurrent neural networks. What exactly is happening? I think at the neuronal level, the transformation functions using the past memory. So that's an understanding of a biological process getting translated to that seemed very different, but it is just a simple understanding translated to a neural level.
And one more thing, sir. How do you feel that will morphology be useful for downscaling or super resolution?
I didn't get you. Morphology means what?
Morphology, dilation. these
Okay.
things.
Image dilation. You want to
Image,
use
image dilation, erosion, this kind of.
suppose,
So there is
you're talking of a scenario when you want to have a morphology, you want to have a dynamic analysis. Then you can also incorporate. I know already. You can use
MorphNet is there.
You can do that. You can have that in the form of. You can use it in terms of gradient variations and enrich. See, if the morphology is changing, suppose I'm laughing, I'm talking, so my intensity is accordingly is going to vary. Correct. So if I'm nodding my head, so the high intensity black is going to come down or the white is going. So now intensity gradient, I can put it in my loss specially. So varying gradients, dynamic gradient analysis, dynamic gradient, I have to capture it and put it in the last one. That's one way of design. That's offhand that comes to me. So if you want to do that, you can do it. There could be other specialized methods for that. You could do for motion pictures. There is a special method for optical flow methods. Optical flow methods are used wherein they are based on specialized laws. So these can be incorporated along with the regular conservation laws. You have the optical conservation laws. So there are optical conservation laws which can be used, and possibly people work on those from the image processing point of view. People do such things. So in the context of dynamic analysis of atmosphere, one can possibly incorporate. So basic physics plus geometrical variation, which is coming to that, one can use that. So now let me, for the next few minutes, I will talk about Fourier neural operators. I don't know whether to say it is really the best method or a hype. Right now people say it's the best, but already it is beaten. People say what SRGAN can give in the context of turbulence, this doesn't give it. So I don't want to say this is the best method, but it seems to have a lot of promise, all that I can say. Fourier neural operators. So what they are, I think, let me skip this basic because I thought this was going to be a separate talk. Just to motivate all these things, I already said all these things to you. So downscaling techniques are used, all these, I think I'll skip all these things. So neural operators have been recently applied to many scientific machine learning tasks involving emulation of physical systems. So operators, neural operators is called. Okay. So neural operators approximate mapping between infinite dimensional function spaces. That's a punch point. That's how they sell it. Between infinite dimension, what is that we are doing by all the methods? We are only jumping from finite dimension to finite dimensions. Low resolution to high resolution. M cross n to m prime cross n prime, where m prime is greater than m and n prime is greater than this. Or otherwise, 10 cross 10 to 20 cross 20. Let's simply say that. So I have a discrete data. So I have a finite dimensions. And I go to 20 cross 20, which is again a finite dimension. Whereas in the neural world, what is being said is you are working in infinite dimensions. Of course, we are really not working in infinite dimensions. We talk about it and finally we have some approximations being done there. But whatever we do in this, supposed to be very, very promising. That's what it is projected as. But already SRGAN has proved in the context of turbulence, the subtleties that it can catch. This did not catch. I want to also put this disclaimer that what I have seen it, I want to tell you so that you will be more careful if you were to use this kind of latest methods for various things. So I will talk of this in the context of super resolution only. That's only limited, but it can be exploited or can be used or can be, there are so many versions of it already in the literature. Last 5 years, so many, multiple versions of it has already come. Neural operators have demonstrated the ability to perform zero-shot super resolution when accumulating physics. That's again a punch point they used for selling. So in fact, that seemed to be good. There seemed to be some promise in it. So what is zero shot means? So you train on a particular course resolution data and you find that it is working for unseen fine discretization also. If you train it on 10 cross 10 to move to 20 cross 20, and if you give a 5 cross 5 and try to get 10 cross 10, it works. If you give 100 cross 100 and want to get 1000 cross 1000, it seems to be working. So that's because I'm exaggerating it so that you will immediately fight with me. So training on 10 cross 10 and getting 20 cross 20, and then you want to do any predictions on 10 cross 10, you'll be able to get it nicely. If I give 100 cross 100 and want to get 1000 cross 1000, claim is that it will work. So that's a punch. So apparently it happens in benchmark problems, and it did not happen in the turbulence context. If it happened, I think by now it would have been the talk of the town. It is definitely in some context has been very, very successful, but not in a general. Therefore, it is called as a zero shot, which is unseen fine discretization of a grid. So from any resolution to any resolution, that's what these are the two punch points, arbitrary resolution levels. It can deal infinite dimensions, which means you can also call it as arbitrary. In a zero shot weather downscaling, a model is trained with small upsampling factor. That is 10 cross 10 to 20 cross 20 it can be. Then the model is tasked with producing high resolution output to an unseen and higher upsampling factor at test time. So some benchmark problems it was promising, and it did not work as good as others. When I say it doesn't mean it is a drawback, it only means that it needs to be further fine-tuned. So don't take it as a drawback of FNOs. I would say that it needs more attention for you to understand more. So now let's look at neural networks in this perspective. What happens basically, it is essentially a neural network only, but generalized at some levels. So basic neural network is I have a data, a vector from Rn, I transform into this, finding this, this is what is finding this appropriate F which transforms X close to Y. That's what a basic neural network is. So you have a discrete data is getting mapped to predicted data, and a predicted data comes. So you have an input vector, you have affine linear transformation, you have non-linear transformation, you have output vector, and that's what is the whole thing all about. You have an input, you affine transform it, and non-linear transform it, and you finally get your output, and see how good is this, and you keep doing. That's the basic neural network. Whereas, if you go to neural operators, what is happening, the thought process is, I want to go little higher. Instead of having a data as X, which is a vector, discrete data, I want to have a better representation, have a function which is mapped. I want to find this transformation, neural operators take a function to a function. Function to a function. They have a vector to a vector, data to data here, function to function. And what is this function? The function, if you can transfer a function, low resolution function, representation in a low resolution, high resolution representation. So what happens? The function is what? If I draw a curve, how many points are there in that? So the claim is that. So whatever resolution you want, when I transform it, I'll have whatever. If I want 1,000,000 resolution, I should get exaggerated version. I should be able to get that. Yeah. Yeah, I will come to that. Yes, I will come to that. When I explain the details of how this exactly happened, the parametric representation comes in the picture there. Right? So what is exactly, that's the punch point. If that's the punch point, then let's look at what is exactly happening here. You have a data. So the data is, what you have here is linear, affine linear transformed and a non-linear transform. What happens here is analogous to that. You have to deal not with the simple data. So just the affine linear transformation is based on the simple data. So whereas here you have to deal with the functions. Therefore, the corresponding operations here is using an integral transform and having a non-linear operator on it, on top of it. So the internal thing that you have here, this is something similar to bias, and that's something looks like a integral equation. It can be Voltaire. People can think now as a Voltaire differential equation, or different gallery of the equations and try to come up with different methods. So I just gave a exaggerated representation of that. It could be, I have here this. If I only look at this, it could be something like
Function US, you are written AS and US both as
both are functions.
same. No, both are functions.
Yeah.
But first is Rn to Rm.
Yeah.
The
Yeah.
second one, it can be Rn to some other thing also.
You can have defined the way you want it. In this function, but this is a low represent. Using 10 points, I would have represented this function. Using a higher number of points, I would have represented this function. This functional representation is a much better representation of that. I can, for having a data represented, I can represent a function using 5 points. I can represent a function using 10 points. So the function, suppose there are subtle variations in that. If I have 10 points, I may be able to better representation for the function in the same space. Right? I am dealing with information in a particular space, infinite dimensional space. In that space, I would like to show 10 points or 100 points. That's what it means. Okay, that's what here super resolution means. Okay, so what you see is, therefore, you see the analogous variation. That's nothing but your transformation. What exactly the same thing happens here? Your nonlinear transform, it is affine transform, is replaced by this integral operator, and that becomes now an integral operator which is continuous. Continuous comes in the picture. Infinite amount of information goes into the picture there. Integral over D. D is the domain. How many points are there? Infinitely many. That's where it differs. That's where it differs. Therefore, it gets an infinite dimension transformation comes in the picture there. So then you transform a function to function. Now, in transforming this, how you are handling this, it seems using Fourier theory becomes very handy. We will see that in a naive way, and that should also trigger rich literature in the Fourier theory may be able to help you to come up with different methods there. So essentially, it is nothing but transforming, given a function V, I transform and get another function U, not a vector to vector. So you have the neural operator being written out in this way. And the number, it's here simply written out. How you write it out in a very simple fashion. So you have several layers coming in this picture there, because you have data at L level is transformed to L+1. There are so many layers at which it gets transformed. So the neuronal layers which is getting transformed is all number of L layers are going to be there. You can have L layers where the transformation is taking place, and this is what is being represented in this context in a symbolic fashion. So let's look at what happens here. You're given a data here. So Fourier neural represent operator, what it would do is, given a function, it is taking to V, and it would first undergo the given information. P here is nothing but you lift the higher the given information to higher dimensional space channel using the neural network P. And you don't accept it right away here. You transform it using neural operators for the number of neural operators. What does a neural operator actually here means? The neural layers, which are called as Fourier layers in our context. So Fourier neural operators, what it does is the information which is already lifted to a higher dimension using a neural network P, that is further processed by Fourier layers. What does a Fourier layer do? The given a function here which has been lifted up, and this is what is the information. This V could have a parametric representation. So that's the information that we give a parametric representation, and it gets into a space there. So finding the optimal theta becomes an issue there. I will show it very briefly. And this V is coming from this. So it could have a parametric representation there. And what we do here is it now expresses in the Fourier, in different Fourier modes, filters out high Fourier modes and takes only the lower modes and take the Fourier inverse transform on it. Now, therefore, you will get the information transform. Whatever you get, it is getting further transformed using the Fourier layer in this fashion. This is the expansion of this layer is this, and every layer would further transform in this fashion there. So what you do after you get this information, once since you took the Fourier transform, you do the inverse Fourier transform on it, and then also you take the information directly so you don't lose the context. So you want to keep the context, therefore you also use the W function which takes the information directly. It could be the conventional linear transformation that you have there, and you transform and then apply your activation function. That's what a single Fourier layer would do, and you can have several such layers, and before you get your output. Now this is going to be a function to a function. So that's what is the thing that we need to know. So we'll go a little more details into this Fourier neural network. So we have seen this is what is happening and how this neural Fourier neural operators are designed, it is this way we said. We will look little more, one more step into it. So we have a Fourier neural operator taking a functional space to a functional space. And that's the cartoon which depicts how it is happening there, convolution layer, a nonlinear operator, all that we have shown. The architecturally, what is happening here is a neural operations are taking place. This is what it is. This integral says there is a infinite amount of information is used there. That's what this says. So what is exactly happening in the Fourier, the way this integral is handled, you take the entire information to the Fourier space. If you take the information to the Fourier space, then we know that you can have, in that convolution operations can be used. It simply turns out to be multiplication. So integration will turn out to be a simple convolution operator in the Fourier space. It's convolved. So then it becomes a simple multiplication. These integrals can be easily calculated. This whole process is calculated very, very efficiently in the Fourier space. That's why we cast the whole information in the Fourier space. First express this integral in the convolution form. Convolution simply becomes in the Fourier space multiplication. So then it becomes a lot easier. The integral simply amounts to multiplying, becomes faster. And you carry all the information, but not in the physical space, but in the Fourier space. So that's happening there. That's what is casting the whole thing to the, sorry. So that's what is taking this information, cast it out in the Fourier space, knock out few things, and then you linear transform all these things that we talk about here. The entire thing is captured in this form. So that's the highlight about it. So now let's, you have the whole thing, once again, recall on that. That's what a Fourier layer would do to the data as it is processing it. This whole operation is efficiently calculated using a Fourier layer. So it becomes very cheap. If you can take the data and project it onto the Fourier domain, convolution is nothing but multiplication, and that becomes very, very fast. And also without losing information. So that's where the people say that it is very, very powerful. And that's the whole thing about, you repeated this from one Fourier layer to another Fourier, this is how the whole thing would look like. You move from the space A, which is a space of functions, to space U, which again is a space of functions, and then you first get your data to your network P, and then Fourier transform, pass it through several Fourier layers, where this is how these operations are done, and finally you pass it through the function Q, where it's mapped back to the dimensions of desired size, and you get your function. And then
That is, we are doing these Fourier layers sequentially, right, one after another. So like, let's say I stop after just one Fourier layer, so then I can that Q, and I can put, and I can get back some function. And then instead of doing one, I can do it after two, or I can do it after three. So I mean, what is the difference? I mean,
so it is exactly asking like how many layers I should have in a deep neural network. Same question. So whether if you are, for your problem, if one layer is good enough, you may get a result in good enough. What is the optimal number of Fourier layers that one could have for a given problem one can think of?
Like hidden layer.
It's like, just like hidden layer.
That's what I'm saying.
Fourier layer is basically the hidden layer, but the Fourier form.
The only thing is you're moving in now in a continuous framework.
And I mean, that is in general for a normal neural network, like as we add more layers, I mean, the general understanding is that we are representing a more and more complicated function. So
And also it becomes a problem may not be tractable, and it may have so many other difficulties coming in. It's really necessary to have that much. After certain redundancy will come. Normally people use 2-3 neural layers. Then they get it. Sometimes you may have to use. So I'm talking at a very base level. People have played with these layers and come up with several versions of it in different applications. So right now, I think that you can decide it based on what is the optimal number of layers. One can decide it. Just as in any other deep neural network, how many layers you would like, how many neurons you would like to have, how many modes you would like to actually do that, what kind of R we should choose. These are all the things which we can work on.
This Fourier layer, I mean, like, is there some design space here, like, or is it like standard? Just like in each layer, we can, I mean, there is a design choice about how many neurons we can put in. So is in the Fourier layer, is there such a choice? Or?
This choice works, and that is not necessarily be the only choice.
I mean, what other choices?
You can think of, you won't have more choices. You should come what you actually see here. We want to knock out higher modes, want to have the lower modes. So this is being done. I would like to represent the whole thing in the functional framework. So one can think of merging various things and putting it as a 2 layers as 1 layer and then do an operational variation right here in R and knock out all this. One can think that way.
It's like hyper-twinning of the layers, no?
It's designing a new layer. What he's saying is, how do can I design a Fourier layer itself differently is his question, correct? You can. See, this is or can I, instead of having a transform, it's a transformation which is taking the continuous data to continuous data. What are the other transformations I can use for taking continuous data to continuous? You can have legendary transforms, you can have Chebyshev transforms, you can have things like that. So wavelet transforms can be used. But we don't know. I just saying it offhand because of the question. The difficulties in executing, because FFTs are there for calculating this very fast. So you need to make sure that if you use some other thing, I should be equally competent enough. I will get much more accuracy. So just that it is using the Fourier basis, so the function can be represented using n number of modes. So can I say, if you look at it from the basis point of view, what is the right basis? Can I not use Legendre basis? Can I not use Chebyshev basis? Why not? So it's a nice question that he has asked. So these are some alternates which immediately come to my mind that one can think of differently and come up with at this level. This replaces by a Legendre layer or a Chebyshev layer, etc. It's possible, right? As long as the idea that is nothing but I need to have basis functions. So the functions are represented correctly in that. So go to the Legendre space or go to this. I should have equivalent results. I should have similar to fast Fourier transform as fast Legendre transform. So whatever I would like to do faster and much faster. So in the process which is not there, maybe you will come up with a new method and it will be nice. So it's quite possible.
And I can use Fourier layers before or after convolution. So the
Fourier layers?
before and after convolution layer.
So right now that's the how it is experimented. If for some reason you want to put where you want to put after Q, you want to put after Q?
Yeah, Q is convolution layer.
Q is the final thing which is lifting it back to the desired dimensions.
Yeah. Is it possible?
For some reason you want, you can do that. You can repeat the whole operations again.
Yes.
Like when you are creating the output, like in the
No, his thing, can I redo on Q again? Redo that again, use some other layers with so this is a template which has been proposed. Now, how you would like to play with the template is up to us. If you play with the template, you have to make sure that my modified template is better than the existing template.
It's mathematically not wrong.
Mathematically?
That is mathematically not wrong. Using.
Of course. See, offhand I said it, you could replace Fourier transforms by Legendre transforms, things like that. Mathematically, I feel it's correct. And you need to prove all the things. Saying that mathematically appeals to me is intuitive, but proving it is important. Okay.
In Bengaluru, Hermite polynomials are very useful to design basic geophysical flows because it comes out as the solution of the differential equation.
Okay. So maybe that may be very efficient in that context.
That's what
That may be very, I think that's a useful suggestion. He says that Hermite layer instead of a Fourier layer in the meteorology context may be more interesting. Good suggestion, because you already seen that it works nicely.
Yeah.
So one can think, and then maybe one of you could come up with that layer, replace Fourier layer by that. So I thought till 1 o'clock. 12:30, is it?
Actually, we had a shortened team, like that is right.
Okay, then I will straight away go to the results. I'll show the results so that you are happy that it works. So here are the results. So that's the low resolution. This is for the Navier-Stokes equation. The input has been out. It has been solved by some method. You are given a solution, and that solution is at this level. And you want to use your Fourier neural network and train it at this level. You get it is trained at this level to go to this level. I think that the resolutions I don't exactly remember. It is trained on this this is the input and you would like to predict it, and this is the target. It has trained on a low resolution. The function, the neural network is supposed to be, after having trained on this, it is now tested on the data, which is on a high resolution. It's able to give that, and it's after having trained only on this, it's getting tested on higher and higher resolutions. So, which goes to say that it is resolution invariant network. It is infinite dimension. It's in principle that it's encouraging. You may not believe it, but that's the published result. So that, which says that you train on this, and this also you're able to get it like that. The trained machine is used for getting that. That's what it is exactly saying, right? So that's what, in fact, it says in kind of the losses that you get. This is predicted, this is target. So the differences are here, and it's very well appreciated. You do the whole thing on this very cheaply and use it at this level. So luxury. So that it looked that it's going to beat everything on the earth, but it did not. So what SR can say, this is what is being shown by different methods for this particular Navier-Stokes solution, which it is trained and tested on this. The functions which have been built is capable of handling all resolutions with equal ease and trying to give the super resolution. In all the cases, these are predicted and these are tested. And we have also generated, we have also tested this out, and we also got good results. That was done by one of my students. We tested a number of simple problems. They all work very nicely. And Chittaranjan recently tested on something on the weather data. I will show you a snapshot, and then. So this is also the result which we have tested it out. This is from the water content which is available in European weather forecast data centers. So low result, it is tested on the trained, the whole thing was trained and worked out. This is predicted, and that's a target, and that's a kind of the Fourier neural net gives a very good result. And later on it was tested on high resolution data or these resolutions, and they give a better predictions. That's a predicted at this resolution, that's a predicted, that's a target. That's the kind of the errors. So even go for final resolution, we are able to get. So, which means that if you have a data of this kind in zero shot, or maybe you may be able to get all these things. That's what it's exactly saying. In these benchmarks, this is a validated result. This is not something which we have tested it out and we get all these things, it is correct. There are cases where they don't work well. So that I will not show it because we have not worked on turbulence problems, but the literature says that it doesn't work that well like SR guns. So in atmosphere or turbulence phenomena takes where the subtleties of the turbulence can be captured by SR gun methods, which I think Bipin is going to talk anyway. So it is not going to be so good. So let me show you this another weather data set where extreme weather forecast was the problem given to one of my students. We wanted to do extreme weather forecast. We wanted to use Fourier neural operators for doing the extreme weather forecast. We haven't gone to the extent of making conclusions. We got some validations which are fine. So in these extreme weather forecast, what we did is we took the temperature data and then from this date to this date and tried to see the super resolution of that. We have not solved the problem of extreme weather prediction, but we worked on the super resolution using Fourier neural nets. So for that, we have used the data from this date to this date. And we have used the information in these cells for training the Fourier neural network. And we are able to get the Fourier neural network work nicely. And when our training was using 16x16 to 32x32 resolution, and it worked well. After having done this, our experiment showed that the same training and same validation, we can reach easily 64 with zero shot from 16x16 to 64x64. We're able to get a good result there. So this is on the real data that we got from the NCAR website, I suppose. This is the data that we got. And a very recent experiment is, I thought we got a very bad result here, but looking at the published results on mean root square error, mean square error, and the mean average errors, that rainfall data that we have used a super resolution analysis, the kind of the information that we got, errors we got seem to be encouraging. So in this case, what we have done is we have used, suppose the full resolution is, I don't remember exactly, that's how much is the full resolution in Chittaranjan here? 129 plus 1, what is that? Something. And then we have a quarter of that resolution here and try to get that. That's a prediction that we make. And these are the mean square errors. And for the training set that we have, these seem to be quite fine with this. This is a zero shot. So in this case, for going from quarter to full is going to be, you have a quarter of this resolution, original resolution, let's say it is X, and this is 1/4 of that resolution, we reach that. And this is 1/2, we get a better mean square errors here. So looking at the mean square errors, which I projected earlier in different contexts, these mean square errors, they were all 1 point something, et cetera. You have seen that. So in this case, we are getting encouraging results. That's the state. And we have to really investigate more. It is a promise. So I thought I should definitely share with this. Many of you possibly may be interested in exploring, if at all you are interested in super resolution. So that's in brief about super resolution. And thank you. If any, I will end it there. If there are any questions, we can take it offline
so much,
for the
sir.
want of time.
Give a big hint. So we can have some questions before going to lunch. Or the questions are exhausted already.
Chittaranjan, you have some questions to me. Huh? You ask. You've already asked the questions.
That's what I, yeah, so questions are exhausted. They wanted to ask, so Dr. Adway already asked.
I should be actually scared of Chittaranjan's questions because he's the one who implemented it. Right. Computational time depending upon the resolution at which you train it. So it depends. So for the Navier-Stokes data, computational time was just nothing, less than a minute or so. But if you have a bigger data set on which you would like to train, I think so. Maybe so, no, for the Fourier version. So before that, we have the P, no, the P will take time. P will take time, and the remaining additional part, hardly it's a marginal inclusion. The P will take time. P will take time. P will take time.
Sir, actually, I had the same question. So I wanted to ask, how about the efficiency of this FNO-based downscaling method?
Say it again, louder.
How about the efficiency of this FNO-based downscaling method compared to like traditional downscaling, such as quantile mapping or even dynamical downscaling? How about the efficiency? Do you see any gains?
There are some comparisons, especially when you go for, see, these are all the data that we have done. If we have not done by other methods, I cannot comment. So, but I can show from the kind of the mean square errors, average, these errors are encouraging. But for benchmark problems, especially the Navier-Stokes problem, excellent. They outperform all the things. For that,
I mean, like excellent in the sense how much, how better? I mean, like for
so
example,
we are able to
in
get
terms of computational time or resources.
resolution, infinite resolution at nearly zero cost, which you will not, in the metrics you want to know, I don't remember the metrics of that. I think we can get it a metrics from that. I think it was very, very encouraging upon the benchmark problems. Say any data generated from simple problems like Navier-Stokes equation, use that data for training. The number of test cases gives very, very promising results. You are way ahead of the regular things. But if you go for real data, still not known.
I had another silly question. So traditionally we call it downscaling, right? But we are actually upscaling it. Why is it called downscaling? When we are bringing lower resolution data to high resolution, so it's technically upscaling.
So maybe I'll also give a silly answer for you. You downscale it, you go down, zoom it in so that you get to see what is there inside it, which you cannot otherwise see. You go down to see what is more deep into that. It's a terminology probably used to see, you get all subtleties when you zoom in. So zooming in is going down. Going down, that could be one naive way of saying it out. So that maybe the people, when they have used that terminology, they may have different reasons, but you're going deeper into that, which you otherwise don't see. You're going down deep into that. So
Thank you. Thank you.